Okay, last week we finished the relative entropy method in mean field limit. Today I start to introduce modulated potential energy method and our new relative modulated free energy method to treat the mean field limit problem. So yeah, we will just start. I will just use the whiteboard, so it can be easy to follow. Let's start by talking about the modulated energy method. I basically follow the paper by Safati. So there's a paper. I think this is so this appendix with drawings. Okay. So let's introduce the setting. The setting is exactly the same, but now we kind of restrict a little bit the setting. So previously, right, for instance, we consider this system. So Wi upon emotion. But in particular, Isafati is paper. So let's focus on the purely deterministic system first. By later, right, when combined with relative entropy, so we will consider stochastic system as well. But for her paper, let's ignore this random noise part first. So usually we just write the time derivative as dot. Okay, so I equals to 1 to n. So all here xti I in rd. So in particular, they choose the following. They consider the following system. Consider so case one. So is k is given by some gradient w. So w is a potential function. So this is the gradient flow case, or you call it dissipative case. Or case two is k is given by some so minus j times gradient w. So j is an antiderivative metric. So j is just an antiderivative. So this case is the conservative case. In particular, right, so you can think like 2D order. So it's a conservative flow. Okay. There's another case also mentioned in the paper, second order system. Is the following. So xi, second order derivative with respect to time. So it's just acceleration. So the acceleration is given by gradient flow. So let's say hi. So this case is the, so this is just our previous system, second order system, by choosing the two-body interaction force by minus gradient W. So W is the potential function as well. So it's Newton dynamics. So this is the setting. So she is considering, but in particular, right? So the assumption, those are the family of interaction kernels. She can show mean field limit. So either, so omega is in the following form. So let's say, so omega is either logarithmic potential or Riesz type potential. In particular, it includes Coulomb type interactions. So omega can include can be Coulomb, logarithmic, or Riesz type interaction. Right. So like case one is, so this omega x is given in the following form, but of course you can add the constant before. You can scale them. Put a constant c here, but let's just write it to be 1. So here the exponent s is positive or 0, but when s is 0 is a trivial case, right? So s is bigger than or equal to d minus 1 and less than d. Or the case B is Gx is just a logarithmic potential. But to make this potential singular, so otherwise you can, that's easy. So we let d equals to 1 or 2. So these are the potentials. So Fati can show mean field limit. And you can also possibly add perturbations. For instance, you can add perturbations here. Like f in some Holder space and in some Sobolev space. So you can, so this is a singular kernel, like in a Riesz type kernel, a Coulomb type kernel, and you can add perturbation here. So maybe let me, so you can add a perturbation. You can add a regular perturbation here. Okay. So as we know, right, so in the first 4 lectures, so formally, if you send n goes to infinity, right, just do formal commutation. So let, so we, so let mu n, so let mu n t, so this is empirical measure, let mu n t is the empirical measure of the particle system. Okay, so formally, right, so if this converges to mu t weakly, so then, so we expect, so this mu t solves the mean field dynamics. So the following system, since there's a minus sign there, I just changed the direction. So here it becomes this. So I call this mean field dynamics. Let's just consider this case. This case, right? So solves mean field. Let's say this is case 1. So for the gradient flow, the limit equation, the limit law mu t of the aggregation type equation called mean field dynamics. So for the conservative flow, you can expect, right, nothing changed but the velocity field. So you just put a, so this is a mean field conservative flow. And case 3 is the following, is this system is the second order system, the Newton dynamics. This is still open, but Savati and Durings, they can show for some specific case, that is the monokinetic case, they can get the mean field limit. So this case is the following. So partial t, in this case, let's change a little bit. So mu, in this case, mu and t should be the following, right? The phase space density, so it's xit vit. So vit is just the time, the velocity, right? Just the velocity. So this will converge to some density, phase space density. And people expect this is just this F solves the famous Vlasov kinetic equation. And now, right, where rho is the spatial density. So what they can do is not this this case, but this case is still open. But they can show for the monokinetic case. So which means the following. So you choose F, the limit guy to be in some specific form. So let's say this is, let me choose let's use their notation. So this F, let's say this F solve the following one. It's given by the following form. So it's mu t. So mu t is the spatial density. And given your position, give you the position x, the velocity is uniquely determined. So it's called monokinetic, right? And position x, the particle can only have determined direction of the velocity. So the velocity variable is fixed and a certain position. So the velocity is a Dirac, which is given by ut. So ut is the velocity field. So if you insert these ansatz like to Vlasov equation, so you will get pressureless Euler-Poisson. So you will obtain pressureless Euler-Poisson system, which reads the following. So first, the spatial density satisfy the continuity equation. Right? This is u, right? U is the velocity field, and mu is the spatial density. Right? It's a continuity equation. And second, the velocity field u solve the following equation. So this is what they can do, but I will give you the details later. Okay. So I want to point out it's a remark. So usually, right, if we write, so usually we, like the Newton dynamics, right, is a Hamiltonian system. You can write in the following way, like if you take xi, right, if you take xi, maybe let's use zi is better. If you take zi to be the position xi vi, right? Okay, so if you write the usual way, we write the Hamiltonian system on Newton's dynamics. So which is given by the following. Let's just using the gradient flow, not a gradient flow here. It's just using the interaction is given by the interaction between two particles is given by the gradient, the negative gradient of some interaction energy. So in this case, it's minus xi minus xj, right? So now I equals to 1, sorry, so j not equals to I. So this is the Euro Newton dynamics. And we can, so this is second order system. So usually we write the interaction, the energy of this system. Right? If we write the energy of this system, they have two parts. Right? First is the interaction energy, then they have the velocity. Right? They have the kinetic energy. Right? So it's the following. So they are the kinetic energy part. So omega xi minus xj, and we plus so this is vi square. So now, right, so usually, right, if you study some study dynamical system, so we can write the system, original system as this, right? So this is a gradient vi hn, right? So vi dot time derivative is minus gradient xi. So you can check hn, right? So actually, right? So actually now, if we write, so if we using zn as like z1 to zn, right? So the dynamics of zn, right, actually is something like j. It's Hamiltonian flow, right? Gradient. So this respect to zn, right? It's a very high dimensional vector, right? Hn. So you can put a minus here, right? It doesn't matter. So J is an antiderivative matrix, right? But this is different, right? This is, you can write this as the conservative flow, right? Hamiltonian system is a conservative flow, of course, but this is second order system. Even you can write write it as a first order system like this. But now, right, this Hn is different, right? This Hn, not just this interaction part, right? There are also the kinetic energy part. Okay, so you cannot using their method to do this case, right? This purely, right? If you consider omega the Coulomb flow, and the velocity is not just it's not a monokinetic, so this is still open. Okay, this is the most important cases, right? People, many people are interested. Okay. So I mean, the goal, right, of course, is to show the convergence. The goal for both the three cases I mentioned, the goal, of course, is still to show show mean field limit. So which is the following: under certain assumption, in particular, the following, right? Initially, the initial empirical measure converge weakly to, let's say, mu0, the initial data. So then we want to show mu1, then to show. So mu_n_t will also converge to mu_t. So mu_t here is the solution to the limit to mean field dynamics. And this is for the interacting particle system, like three cases before. Okay, as I said, right, the weak convergence or some type of weak convergence of the empirical measure towards the limit is equivalent to the propagational chaos. So as we talk about in the lecture 3. Okay. So there are several results before, but I won't talk a lot about that. There are many results. So you can see the previous lecture 3, the slides in lecture 3 for details. But there are many people studying like both the gradient flow type mean field limit or conservative type conservative flow type mean field limit. So in particular, right, so for 2D Chauchet literature, like Chauchet and Goodman, so those are basically on the 2D Euler. And later, right, so O'Hare and also Carrillo, Troy, and O'Hare. So this is so they study like the deterministic system, but the kernel K is given by gradient of some. So the kernel K is given by minus gradient W, and W. So this the singularity of the kernel is weaker than Coulomb. But the Safadis paper can exactly treat a Coulomb case, but while previous paper like by O'Hare in particular, so you cannot cover. So they use the stability analysis based on Wasserstein distance. Wasserstein distance actually is Wasserstein infinity. So Coulomb case is not covered. So there are also other results. For instance, by Carrillo, there are actually many. I just like in Berman. So based on gradient flow. So I think this is based on gradient flow techniques. Using the convexity, for instance. Using convexity argument. Okay, so there are many. I just want to list this. And also, so like the paper for second order system, right? For second order system, these are all for first order. For second order system, so my paper, so which means the limit equation, so is the Vlasov equation. In this direction, right? Excuse me. In this direction, there are several results. Right? For instance, I also listed in my previous slides. I think, and also Superior Emmanuel and myself. So for second order system, so this is where we use relative entropy, as I talk about in last two lectures. And there are also another type of result on mean field limit. I didn't mention, but maybe let me just mention here. So it's the cutoff type result. So what does this result looks like, right? Since we don't have enough time, I will just mention here. So later I won't mention this type of result, but they're also very interesting as well, and it's very useful actually in physics. Right? When people really doing physics, maybe this is a routine way to do that. So it's like this, right? So let's consider, let's just rewrite the second order system. In the mean field scaling. So, okay. So as n goes to infinity, right? So this is the kernel K, or let's just using the kernel K to keep our notation short. So we will get the mean field equation, right, in the limit. So there's one way to do that, but okay. So for a lot of settings, right? So K, for instance, in plasma physics, K is singular, right? So let's just treat this case in 3D. And this is really the Vlasov person. So in this case, Kx, right, is just this, the Coulomb force, right? As I said, right, so if you just want to exactly use this system, exactly using this system, and you want to get the convergence to the exactly the Vlasov person system, this is still open. But there are some results, right? So they try to regularize this kernel K. So they regularize this kernel K, that let's say by a parameter delta. So this delta depends on n. So Kx in particular, right? Maybe I use epsilon n. So K epsilon nx, right, is some regularization. Right? It can be like a convolution. Let's say phi. So phi epsilon nx. So phi is a modifier, and you regularize this kernel like phi is something like modifier, right? Modifier. This is one way, right? You can even just like for the you can just do this type of cutoff, right? So let's say this is Kx, right? This is K, and you choose epsilon n here, right? Epsilon n maybe is the some distance, right? You can some critical distance you choose, and you just do this cut, right? So as x goes to 0, right, original Kx blows up, but you just choose a critical distance, epsilon n, right? When the distance is smaller than epsilon n, you keep them constant, right? So so you can just like do regular. just do this type of cut as well, right? So so if or then it's equals to a y. So okay, sorry. So equals to some constant, right? Some how to write that? So if it's smaller, right, you just fix a constant. Maybe not a constant, just how to write that? Maybe I should write if x is smaller. So then you just choose them to be the value and x. So it should be x over x. Just do like that, right? So using like this type of cutoff, right? So you can show the convergence. Like you can show the convergence of the empirical measure towards the limit f, like almost surely, not almost surely, like in large probability, like in this way. Okay. So for this type of result, so let me go back to my yeah. So for this type of result, there are many results. So for instance, just list several. In particular, in this direction, there are many results done by Peter Pico, and his collaborators. And also the many others, Carrillo, I think Samir, and Troy, etc., and Django Liu, and etc. Also, there are the very long time ago work by O'Hare and Japan. So maybe this is the first result. Okay, maybe 7. Okay, I won't talk about this cutoff type result. So this type of result is basically you play around with parameters epsilon n, and people believe, for instance, so epsilon n can be large, it can be and small, maybe even smaller than this. So D is the dimension. For instance, in dimension 3, right? This is so you just so this is the critical distance, right? You like your average. If all the particles are arranged evenly on a size 1 box, so this is the typical distance. So usually you should choose this epsilon n as small as 1 over n to 1 over d. But previous result is not that good. So you should choose epsilon n is slightly bigger than that. But it seems recently there are improvements in that direction. I forgot the name, but it's probably Pico student. So they can improve this cutoff parameter epsilon better than 1 over n to 1 over d. So yeah, so this is also a one direction in the infield limit problem. Okay. Yeah, so let's move on. So for this work, so later we'll talk about our new interpretation and the way to include more general interaction kernels, and also how to treat the stochastic system and vanishing viscosity systems. But now let's just use very easy computations to show the basic idea of the modulated energy method. The idea is very simple. as modulated energy method. So this is also a weak-strong type, weak-strong uniqueness principle, or weak-strong uniqueness, or weak-strong stability type argument, as I mentioned for our work, like on rest of systems. But here, right, like we use relative entropy, but here they, Durings and Sarfati, so they use Coulomb or Riesz type metric. So they call Coulomb or Riesz type metric. So this type of metric is like following, right? Let's say that omega is the potential, right? Omega is the potential we write before, like Coulomb potential or Riesz or logarithmic potential. So we can define, we can compare two probability mirror, mu and mu, like the following way. Maybe let's write omega here, but we can ignore that as well. So when I write this, let's assume mu and nu, these are very regular. So you can, there's no problem on the so this formula is well defined. Let's assume everything is well defined. So we can write the metric like the following. Okay, so this is a Coulomb type metric they use, but as I said before, so if we formally take the Fourier transform, right? So this is just omega hand psi and mu minus v square, and we integrate in psi variable. So if omega, the Fourier transform of the not omega of W is positive, right? This is always positive, and there's no problem to show the positivity of this quantity. But you will see, right? If this mu, right, is empirical measure, and since there's no self interaction, and if two particles are very close, right, it blows up. So if you consider singular kernels, there are problems to interpret this quantity, right? So there's a procedure to renormalize this quantity. Then it's observed by Sarfati in her paper, and I will show you later. But this Coulomb type metric, right, is basically a Fourier norm, or a norm in some Sobolev space, right? It's some negative Sobolev norm. I will show you a very easy commutation. So this is a motivation for their method, for their modulated energy method. It's weak strong uniqueness principle. Let's say just for this mean field dynamics, let's just choose a very specific one. Since this is, so we change a little bit. Mu. So we just choose this one. So let's even choose omega is the, let's choose using the Coulomb case. So in this case, omega is the Coulomb kernel, is the Poisson kernel, which is either x d minus 2, or right in, so d bigger than 3, or in dimension 2 is log x, it's minus log x. So in this case, right, omega is is a fundamental solution to the Laplace equation. So in particular, right, if we choose H, right, we write H mu. So we write H mu as the potential generated by the distribution mu. Excuse me. So we write this, right? right? H mu is the potential generating by the distribution mu. Okay, so of course, this is like a first lecture, first class in PD. So we have this CD mu, right? So right, omega is just a CD Dirac, right? So omega is the fundamental solution, right? So let's compare two solutions, right? Let's compare two solutions, two weak solutions to the mean field dynamics. Let's call this mean field dynamics. Okay, so and we're a little bit fast, but anyway, so using the Coulomb norm. So which is the following, right? Let's say, so this is omega, right? And so D mu 1 mu, so n time T, mu 2 n time T, this is X, D. So we want to compare this quantity. So this basically, right, is just mu 1 T minus mu 2 T, and this is omega, let's say square. And we want to evolve this quantity. So there are problems here, but you can show, right? For instance, right, if omega, right, at least for Coulomb force, for Coulomb, if omega is a Coulomb interaction, so this quantity, if mu 1 T, mu 2 T are nice enough, so actually this is always positive. Right? This is not a problem under certain assumptions, right? Because we know, right, if you take the Fourier transform, this actually is x to 2. This is, sorry, this is positive, right? That's not a problem as long as mu 1, mu 2 are regular enough. Okay, and this can really measure the weak convergence. Let's leave this as an exercise. You can find this in During's paper, his Science journal paper. So this is the following things. So maybe we put a letter. Yeah, maybe we put this letter and just to tell you the idea first. Okay, let's write, maybe let's just write mu equals to mu 1 T minus mu 2 T first. Then what we want to write is to reinterpret, rewrite this quantity. Let's maybe we should change a little bit. Let's assume mu is a general mirror, right? It's just a mirror. It maybe has a sign, right? Not just a probability mirror, a general mirror. Let's say radon. Okay, so as well we can write h mu equals to this. Okay, so and of course here this is true as well. So now this quantity omega x minus y d mu x d mu y. So this equals to this, we claim, right, this equals to, we can rewrite this as the following representation, right? So you can always say this is positive, right? It's because it's an integral of a positive quantity. Right? How to see that, right? You can see this using Fourier, and you can also see in the following representation using the harmonic representation. So how to do that, right? So this equals to omega convolution mu x d mu x, right? We integrate this y first, right? So we get a convolution. So omega convolves mu is just the potential, the Coulomb potential generated by the distribution mu, right? and this is d mu x. By this equation, by the Laplace equation, we can write mu as the following. So h mu, so over CD. Right. So we just using that equation. Write mu as 1 over CD, right? Laplace h mu. So then we can integration by part, right? So using integration by part, right, we just get this, right? Integration by part. So using this way, we can represent this quantity. We can represent the Coulomb norm, like using the potential, right? We can get this. Okay. So now let's introduce like stress energy tensor. So basically, so this is a quantity you can show, right? So this quantity, you can use this quantity to measure the distance between mu1t and mu2t. And so if we can, so it's again the Vickers strong type argument. If we can evolve this quantity and complete the control the growth of this by Gromov, right? We can get a big strong uniqueness result, right? And if we adapt this to multi-scale version, right? Like mu1t now becomes empirical measure, and mu2t is the limit, and we can hope to get a mean field limit type result. Yeah, the basic idea is exactly like the relative entropy method we used. Okay. So the following, I just want to introduce several notations to complete the commutation. So it's the following, right? It's h mu, h mu. So this is just a matrix, depends on h mu. It's a function. So h, right, h mu is just omega converse mu. So h mu is so h is a scalar, right? It's a scalar function. It's a potential, and so here when I write h mu put in the bracket. So this is a metric tensor. It's like d by d metric tensor. So I write ij here. So the ij component is given by 2 partial I h mu partial g h mu, and minus this delta ig. Okay. So then we can take so for regular, let's say if mu is regular enough, right? So we can take derivative, like second order derivative of h mu. For regular enough mu, so we can take the divergence of this metric tensor. So when we take the divergence of a metric, so it's like a d by d matrix. So this meaning is just we take the divergence of the rules. So we take divergence of first rules, right? Give you one scalar function, right? Take the second, right? Give you, so this in the end we get a vector. So you can do the computation, but the result is just the following. The following is just this. And if we use the Laplace equation, right? So what we get is just this. Okay. So we can use this. Now we can just compute, right? Just compute the evolution of this quantity. We can just compute the evolution of this quantity and see what it goes. Okay. So let's just compute that. There's a d over dt. So then quantity is omega x minus y, right? So here is d mu1 mu2 t x d mu1 t minus mu2 t y. So by the so this is so this quantity, right, as I said, right, so it equals to the following. It also equals to gradient, let's say gradient h1 minus h2 square. So here, right, hi, so here hi just equals to omega convolves mu I equals to 1, 2. This is just a second, the previous re-representation, right? It's exactly the same. So it's not exactly the same. This is there's a factor 1 over CD there. Okay, so there's a factor 1 over CD there, but yeah. Okay, so let's do this computation. So what do we get? Okay, so x, so by symmetry, right? So omega is an even function. By symmetry, we can just take a derivative with one of them, right? With variable x. So but we need to put a 2 there, right? So there's a 2. So then we have 2. Excuse me. Yeah, so it's CD. So there's no CD. I change a little bit. Yeah, so now it's h1. So we take derivative with respect to this variable, but the symmetry, right? So there's a 2 there. So what do we get, right? So so here, right? So this and this one, we get h1 minus h2. h1 minus h2. So then we add time derivative mu1 minus mu2. Okay. So then we're using then we're using the equation, right? So it's h1 divergence mu1 gradient h1 minus mu2 gradient h2. So here let's change. Let's do one step of evolution. Sorry, integration by part, right? So we get this. So now we get mu1, mu2. Okay. So then we can interpret one term, right? So it's something like this. So here we take minus mu1 gradient h2, right? Then plus mu1 gradient h2. So then we have terms. We have two more. We have two terms. H1 minus H2 square integrate against mu1, right? So then I guess it's 2. Excuse me. Let me just check that. So this should be plus, right? So then, so minus 2 H2 H1 minus H2 mu1 mu2. Okay, so the first term is always positive, right? So this is always positive. So this is positive, right? So we can just throw away this term. And this term looks very familiar, right? So what is this term? So H1 minus H2 is the potential generated by mu1 minus mu2. So we can use the we can use in the divergence formula here, right? So, but there's a 1 over CD there, right? So there's a 1 over CD. So here is gradient H2, but there's a divergence H mu1, so it's just H1, sorry, it's just H1 minus H2, H1 minus H2, okay? So this is the divergence of metric tensor as we used before. So here, right, so actually we can almost complete if we made very strong assumption, like let's say if mu2, right, one of them is very nice, let's say mu2 is nice solution to the mean field dynamics. So H2 equals to omega convolves mu2. So if mu2 is nice, right, so H2 is nice. So let's say H2, you can take second order derivative of H2. So let's assume this is bounded, like both in time and x, right? So, but we probably don't need that strong. But let's assume these are gradient, the second order derivative of H2 are bounded. We can integration by part, right? So we can remove the divergence to gradient H2, and then we pull out the gradient, right? So there's a constant C, which is 1 over CD or and other factors which we are not really care. So then here there's a second infinity norm of H2. So then, so we need control terms like involving H1 and H2, involving in the terms purely in the metric tensor. So what's the metric tensor, right? It's just defined like this, which only involves the first order derivative. So up to a constant, so this is just H1 minus H2 square, right? Because right, this is square term, right? This is square term, right? Up to a constant, this is always true. So so what do we have, right? So what do we have? Sorry, let's just maybe it's a constant over CD, okay? Because CD is always there, and here it seems they have also 1 over CD. So I want to keep it there. So if we combine all the computation, right? What we get is something like right, yeah, it's something like the previous mu1t, right, mu2t omega square. So if you take d over dt, so what we get is just, I mean, this part, right, is just this, right, just this norm. So what we get is c is a constant, and here is itself. See, here is omega. So then we can estimate this, right? Exponential, right? So c, so t, but this can be relaxed, right? For instance, to be the integral, this can be like s. So mu1 0, mu2 0. Okay, so this is the Weierstrass stability result. And this gives you the idea actually to Safati and During's result is the modulated energy method. But that's not done yet, right? Because here mu1t, mu2t are like regular mirrors, right? For instance, they are bounded. But when we do mean field limit, this is not true, right? This is far from true because we're starting from like empirical measure. So those empirical measure, right, even is stochastic, right? They might be have some, so that it's not like length regular. Right? So the counterpart for this, become the following. I mean, you can formally write length in her paper, it's written like Fn xn t mu t. So in her paper, so the discrete part, so the discrete counterpart becomes the following. So let's say xn is the configuration, is one configuration of the particles, of all the particles. So x1 to xn, right? And again, the empirical mirror is just x1 t, sorry, not this is 1 over n I. So is this, right? So if we can change change her notation a little bit, right? So she used this, like to compare the distance between particle system and the limit, right? So this is the notation appearing in her paper. So omega. So then we integrate with the. So but we can change a little bit. So n mu t x. So d minus mu t y. So this is if we normalize this, right, it becomes a natural analog of this metric, right? So here we slightly change this, right? Instead of using xn t, let's using mu n t. So we just because the empirical mirror, right, give you all the information on the particle system. So let's using mu n t, right? So here we just divide by n 1 over n squared. Right? Previously we just divide 1 over n squared, so we can get this one. We can get the following one: d mu n t minus mu t x d mu n t minus mu t y. Okay, so this is the counterpart, right? So nothing new, right? We just change like mu1, mu2 to the empirical measure and the limit, right? So but there's a problem here, right? The removing is like we remove. We remove the diagonal. So this is very important, right? Because right, when we're using interaction energy, right, you can try to expand these things. You can try to expand these things. They are quadratic. These are quadratic diagonal terms. So if we expand these things, right? So what do you get, right? There are four terms, but there are terms like this, right? There's one term. Omega x minus y, d mu n t x, d mu n t y, right? So if you do not remove the diagonal, right? So then what does this mean, right? You can explain everything, and this means the following. Right. So this is the total interaction energy of the n-particle system. But as we know, right? So there's no self-interaction. So the right way is to remove all the diagonal. Right. So I is not equals to g. Then you run the all summation from I equals g. So everything not equal, right? So you must remove the diagonal. But the problem is, right, if you remove the diagonal, right, this quantity is not necessarily positive. So it can be negative as even, right? But that's not a problem. So actually, this type of things is probably called asymptotic positive, right? So this quantity is not positive, but as n goes to infinity, right? So you can show this is positive. There's a high order term like O1 will be really small when n goes to infinity. This actually is a critical part, one critical part in his paper, and also in our paper. Okay, so this is the quantity. So the main result is the following. I think I can just copy here. So I think I can copy here. Yeah, I can copy here. So this is her main result. But since we didn't consider the perturbation, right, you can basically ignore this part. So her method can be adapted to like regular perturbation. Right? You can consider more terms like f terms here, right, which is regular, its holder, and in some sublet spaces, homogeneous sublet spaces. Okay. And this is a weak strong type. Oh, here G is just omega. This is just omega, just W, just W. So every other things are the same, but I can change this a little bit. So mu n. So 1 over mu n here, n square here. So the assumption is like, okay, we assume a priori we have solutions of mu t which satisfy some bound. Okay, it's a regular solution, right? So because everything is based on like weak strong type things, so then we can evolve the Coulomb type norm, right? So here is Fn xnt, right? This is the quantity we write before, right? It's just this quantity. Okay, so we can evolve this quantity by Grunwald, right? This is the last factor, C2. C2 depends on many things. And here is a factor n2 beta. So here beta is less than 2 if you normalize by n square. So this becomes very small quantity. So this will give you mean field limit, right? If you initially choose well-prepared data. So if initially you choose the empirical measure have convergence such that so the normalized such that this quantity, such that the quantity we define here will converge to 0 initially. So then their main result says, right, you can propagate this quantity and have the same thing for t from 0 to capital T, right? For all time up to time t, capital T, and then you can get the propagation of chaos, right? So the exercise you can check, and also you can find in During's paper is the following. So here, right, this result, let's say this equals to Fn mu n mu 0. Okay, so it's just a quantity I defined here. Okay, so they call this result, they call Fn mu n 0 mu 0 equals to just x not equals to y. So it's the integral of diagonal things. So let me just be a little bit lazy. So this is square xy. So you integrate with the tensor product of mu and 0 and minus mu 0. So you need to assume the convergence and initially. So then you propagate this. So so they call this type of data. So you need a real prepared data. Well-prepared data. So not all data will satisfy this, right? You need well-prepared data, And this in particular, it can be get if you have the following. So if you have the convergence of interaction energy, automatically you will have well-prepared data. So if so here is just I think it's just 2 equals to J. So if you have convergence of interaction energy, so you will have well-prepared data. Then, okay, so this is in like you can find in During's paper. Okay. Okay. So that's the idea, right? That's the idea. That's the main result, right? For the first order system. So for the first order dissipative or conservative. So later I will talk about our our interpretation of this method. But let me just explain a little bit about so how they do this, right? How they reinterpret it. So in the discrete case, right? So there's a problem, right? As I told you before, right? So so this quantity Fn issues. So this Fn mu n mu, so it's integrate on this. So here is omega x minus y d mu n x minus d mu x. So d mu n y minus d mu n, sorry, d mu y. Okay. So here, right, so you remove the diagonal, right? You cannot just like using the previous y to do that, right? But you can still expect, right? You can still expect this metric, this Coulomb type metric can be represented in some potential, right? You can still expect this can be represented like something h mu minus mu squared. But this is not true, right, anymore. But you can do some normalization. You can do some procedures to pull everything back, right? So this is so I just basically explain so her idea. So then we will go back to our method. So the method used here can be reinterpreted using Fourier point of view. But to do that, we still need some like a very delicate intermediate step like truncation things, which also used in Sabati's paper. Okay. So this is the following way Sabati did in her paper, right? So instead of considering, right, so the charge, right, just enter n point, right? So she introduced some regularization, but these are intermediate interpretation, right? So let's say So the electric potential is the following. So Hn mu Xn. So let's using mu n. So this is electric potential. So it's not exact potential. It's kind of the relative potential. So generating by the empirical measure and with the reference limit mu. Okay. So as I said, right. So you can expect, right, the previous Fn mu n mu can be represented by this. Up to some constant, right? So maybe like CD, but this is not true. What can be done is the following, right? Because why it's not true? Because so this, if you take the divergence of the Dirac, right, and point xi, right? So what do you get, right? So but this can be corrected by using modified Dirac methods. So instead of just consider a Dirac and a point in her paper, like she consider like modified Dirac mass. Like the mass instead of concentrated at one point, now it concentrated on a sphere. Like it's a sphere like with center xi with a radius eta I, and this eta I is changing with respect with respect to the indices. So eta I are not chosen a priori. So eta I is like it's not like the previous cutoff parameter people choose, right? It's like intermediate step things, which will depends on like minimal distance, for instance. Like, okay. So the correction is the following, like we choose, so we choose a parameter. So those are all positive. So now we can consider, so now it's like, okay, originally, right, it's like the charge is here, but now you like, you push the charge right here on the sphere. So here is xi, here is eta I. Okay, so we consider like truncation one, right? Truncation electric potential. We call this H eta. So it's something like this. So now it's a regularized Dirac. It's regularized Dirac. So here delta xi eta so is a uniform mass mirror of mass 1 on the sphere on this sphere. Okay, so now, so then we can reinserting the diagonal terms. So now then this Fn, so mu and mu, so will become this. sorry. So mu n minus mu x or y. Then take the difference. N square gx minus y. So is Dirac delta xi eta I x d delta xi eta I y. So this is like so this term, right? So this term we insert back, right? We insert the diagonal terms back. So then later we take out this insert terms, right? So then we get the terms, get the Fn without, so this, in this summation, so no diagonal terms, right? And this this way, right? So in the first integral, in the right hand side, there are diagonal terms, and the last term is just we put away, right? We remove the diagonal terms. Okay, so then the first term now can be represented, right? So now everything is regularized, right? We can using the harmonic representation. So it becomes hn eta mu squared, and then the last term can be just can be computed. Let me see. Last term is like a CD over n squared g eta I. So g eta I is just, sorry, is omega, is some abuse of notation, is just the value of omega and the radius eta I. Okay, and this term, right? So as long as we show the last term is in the high order of n squared, right? We can show this quantity is asymptotically positive, right? So this term, right? This term is positive, and as long as we show this is has a lower bound, right? The lower bound is vanishing to zero as it goes to infinity. We can show, right? So Fn is effectively, right? It's can be used as a metric because it's at least is asymptotic. It's asymptotic positive, right? Then we can also show the, so this quantity measurize weak convergence at least. Okay. So this is a way like give a renormalized meaning to the previous identity, right? Previous identity is easy, right? So if omega, if everything is nice, if mu is nice, just this. Okay. Okay. Yeah. So this is one critical part. There's another critical part. So let me, so another critical part is following. So if we look at the previous computation I showed you, if you look at the computer, this computation I showed you, right? Okay, so this is the time derivative of the norm, the Coulomb norm, right? So it's a time derivative of the Coulomb norm, and this is the last term. And let's just see this one. Because the first term you can just throw away, right? It has a sign. And if you look at this term and using symmetry, so here basically you can using symmetry and you can exchange the rule of 1 and 2, and you can basically get the following terms by a lot of commutations. I will just copy this commutation from her paper. Okay. So this is a critical term we need to control. Sorry. So it's terms like this. So here is h mu minus h mu n x y. So here is x minus y. Now it's d mu minus mu n x. So if you take the evolution, right? If you take the evolution of h n mu, in the time evolution of this quantity, so you have many terms, and sometimes you can basically store away, but there's a critical term like this way, and we need to control this term. Okay. So here, right? So this is also the critical things appearing in our work. I will explain our way to do this, to treat these things later, like using a unifying the framework. But the observation, right? The theory or the key proposition there is the following one, right? So we need to control this term by Fn or Fn plus some high order term. And so if mu, right, if mu is good, right? So I think I might make mistake here. I think I make a mistake. So here is not mu n, it's just a mu. The symmetrization is on x and y, it's not on mu1, mu2. So if I made a mistake, let me know. Okay, anyway, so here the terms we need to control is like the following one. So it's a relative nice function psi1 minus psi2, and we integrate on some like this term, right? Let's just let's rewrite that. So the things we need to control is the following. So x is not equal to y. We integrate all those things in some by removing the diagonal, right? So there's no diagonal terms. So we need to control terms like this. So gradient W, right? W is like Coulomb force, Coulomb interaction, right? 1 over x2 square, right? In dimension 3, and like W is, so usually, right? So gradient W is more singular, right? Is 1 order more singular than omega. But the problem here is the following, right? The following. So we can use the regularity of psi, right? Usually psi is better, right? Because the integral, right? So like h mu, right? Mu is the limit. So h mu is a convolution. Usually h mu is nice. So we can using the regularity of this psi function. So basically this x like w. I mean, this is just the intuitive explanation. And so if we do the integral, right, we can just write Fn minus mu is the same. So basically this term behaves more or less like Fn itself. So we can control the right-hand side. So this term is very close to Fn mu and mu up to a higher order terms. So basically you can control these things like C and plus some high order term is as n goes to infinity, right? This term will be small. So you can using Grunwald inequality, right, to complete the proof, the growth, right? Can bound the growth of Fn. So once you have well prepared initial data, you can do that, right? You can get the mean field limit. Okay, so this is the key. This is the key estimate. There, I already over time, but maybe I just spend 2 minutes on the quantity they used to do the monokinetic case for Euler-Poisson. So that case is basically, I mean, it's just adapt the modulated energy method for the monokinetic case. Okay. So the Euler-Poisson, the pressure is convergence. Convergence to Euler-Poisson. So in the mono so in this case, so as let's say using Zn as x1 v1, xn vn. So of course, right, vi equals to is the velocity, right? Vi is the velocity, right? Xi is the position. Let's assume, right? So in the limit, so ft xv is given by mu t x delta. So the velocity is given by a function, so utx. So everything is, the setting is like before, right? So what the quantity they used, right, is the following. So modulated energy. So now you should both consider, right, the position and the velocity. Maybe let's put mu n as well. So now mu n is just this. So mu n, and so now, so the ansatz, right, is mu t, and also ut. Right? So mu t is the phase space density. So ut is the velocity field, and position x, right, is the velocity field. So we use this quantity to do Grunwald type things. So Fn is exactly like what I defined before. So then Durings and Sarfati can get the mean field limit result again, right? Starting from something well prepared data. So the statement is more or less the same. And you can look at their paper for details. And I will just stop here. Okay. So any questions?